Hi everybody, happy Monday. Happy first snowy day of the year. This is lecture 30. We're going to be discussing Stewart section 4.7, which is antiderivatives. We'll be discussing that again on Wednesday, and I think you don't have recitation tomorrow, right? And then Friday is our exam. I'll be posting information about the exam tonight, I think maybe tomorrow morning. It'll be on chapter 4. It's this coming Friday. Okay, well, our first part of the meeting is just an introduction. I'm going to define the word antiderivative. So here's a phrase. Now, if you just speak this, it's going to sound like nonsense. It says f of x is an antiderivative of f of x. Now, if you speak it that way, you miss the whole point of this, of the definition. So this is capital, and this is lowercase. For now, while we're doing the introduction, I'm going to be using capital letters and lowercase letters. So I would say capital f of x is an antiderivative of little f of x. Here's the meaning. It means capital F prime equals little f of x. That is, little f of x is the derivative of capital F of x. Now, I don't have room down here, so I'm going to put it over here. Diagram. There's a way of doing this horizontally that doesn't take up as much space, but I'd like to do it this way. Just have capital F of x and an arrow pointing down to little f of x. That arrow is the take derivative arrow. So, this is the definition of antiderivative. That's all we have. So, for example, is capital F of x equals x cubed. Actually, I'm going to say is capital F of x equals, x to the fourth. Is that an antiderivative of little f of x equals x cubed? So that's a question. Well, we have no tools for finding antiderivatives. So you can't say, well, I've got an antiderivative, it's not this one. Well, our only tool is this definition of antiderivatives. So what we have to do is we have to check. So we have to find capital F prime. So that's the derivative of x to the fourth, and that's going to be 4x cubed. Oh, that's not little f of x. So the answer is no. Now, what's wrong with that result? So in other words, I'm going to think of this as guess number 1. I'd like to make another guess, but I'd like the next guess to really be good. I don't want to sit here guessing all day. So what was wrong with this guess? Cooper?
Big F of x doesn't end. Well, big F prime. Well, little it's the wrong.
It's like
coefficient.
Yeah, so somebody else explain this. a different way maybe. Say, try this, Cooper's mentioning the coefficient. Let's just say off by a factor of 4. That's what's wrong. We're supposed to get x cubed and we got 4x cubed. So let's make guess number 2. Let's make capital F of x be x to the 4th over 4. So now let's find capital F prime for that function. So check. Capital F prime of x is the derivative of that baby. This gives me a chance to rant about things that look like quotients, but you don't need the quotient rule for. This looks like you're finding the derivative of a quotient, and you are, but if you use the quotient rule, you're working way too hard. And overwhelmingly, students use the quotient rule. And sadly, a lot of students who use the quotient rule make a mistake, and so they end up having a derivative that should be really easy. They've taken a hard approach to, and they've gotten the wrong answer. So the smart way to do this is you pull the constant multiple out front, and then you're just finding the derivative of x to the 4th. Use the constant multiple rule. And so I get 1/4 of 4x cubed, and so I get x cubed. So the answer is yes. This is what's called the guess and check method, and it's a great method. There's nothing wrong with this method. We're going to soon enough we're going to be learning rules for finding antiderivatives. But even when you have a rule, you're going to want to check it. You're going to maybe want to use the rule to give you what you think is an antiderivative, then you're going to want to check it. So the guess and check method is really good. I've mentioned before my experiences in undergraduate calculus. I remember that I only really began to get comfortable with derivatives when I started learning about antiderivatives, and I had to do all these checks. And every time I did an antiderivative, I would check it. And you'll learn that you got to revisit all your derivative rules, and you got to do them correctly. Here's one. Is capital G of x equal x to the 4th over 4 plus 17? Is that an antiderivative of little f of x equals x cubed? Well, that's a guess. So let's check. Capital G prime is going to be the derivative of x to the 4th over 4 plus 17. Now I do these derivatives separately. I know what the first one is going to give me. It's going to give me x cubed. The second one is going to give me 0, so that's x cubed, and that's f of x. So yes. Wait a second. I thought we already had the antiderivative of x cubed. I thought the antiderivative of x cubed was x to the 4th over 4. Now I'm saying the antiderivative of x cubed is x to the 4th over 4 plus 17. What's up with that? Yeah.
The derivative of any constant is 0.
Right, that's why this worked, but what's up with, this thing coming to the party as the antiderivative of x cubed, and this thing coming to the party as the antiderivative of x cubed? I mean, who gets in? Why?
Because the derivative of a constant is 0.
Yeah, but how does this square with the definition? Let's go back and look at the definition. It doesn't say the antiderivative. It says an antiderivative. That's subtle. So functions can have many antiderivatives in general, and they do. So a particular function has a single derivative, but has a whole family of antiderivatives. So capital F of x equals x to the fourth over 4, and capital G of x is x to the fourth over 4 plus 17 are what are called particular antiderivatives of little f of x, which is x cubed. Now, what's called the most general antiderivative, or the general antiderivative, so the general antiderivative of little f of x, that's x cubed, is what's called a function form. X to the fourth over 4 plus c, where c is a letter that can represent any real number constant. So it represents an unknown real number constant. So let me go back and talk again about this idea of what's called a function form. It's not the same as a function. So for instance, this is a function. I can say let x equals 2, and what's y going to be? Well, y is going to be 2 to the fourth over 4, so that's going to be 16 over 4, so f of 2 is going to be the number 2. Going to be the number 4. In this function, what's capital G of 2? Well, it's going to be 2 to the fourth over 4 plus 17, so that's going to be the number 21. These things are honest functions. You give me an x, I can give you a y. This thing is not. You give me x equals 2, and I can't give you back a number because I don't know the value of c. So that's what we call a function form. Notice capital F is one of these babies with c equals 0. Capital G is one of these babies with c equals 17. So every particular antiderivative has to fit the form of the general antiderivative. And you say the general antiderivative because there's just the one form. All right, meeting part 2. We're going to make build a simple list, or build a list of simple antiderivative formulas. Or I'm going to say basic antiderivative rules. So here's one. I want to call this the e to the x rule. So an antiderivative of little f of x equals e to the x is what? What goes here? I should say a particular, because I want to not deal with the plus c. So a particular antiderivative is just e to the x. I want to not deal with the plus c's. Now let's remember why this is true. I want to think of two copies of this. Up here is capital F of x is e to the x, and down here is little f of x, which is also e to the x. And to get from this upper graph to the lower graph, you find the derivative. I'm drawing that because I drew that kind of picture before when I was introducing the derivative rule for e to the x. I said it's not a proof of this rule, but it makes sense. So I drew this graph, and I put tangent lines on it, and I considered the slopes of those tangent lines, and the numbers that were the slopes of those tangent lines kind of agreed with the numbers that are the y values of this graph. So this derivative rule makes sense, and the fact that we can turn it around and talk about antiderivatives makes sense as well. All right, now let's keep going. Oh, I'm going to do this all over here. No, I'm going to do it over here. Find an antiderivative of e to the kx. So find an antiderivative, so not the general one, of little f of x equals e to the kx. Okay, well, we've just seen that the derivative of e to the x is e to the x. So anybody want to hazard a guess? Raise your hand if you know, if you want to make a guess. Yeah.
K root of e to the 2k.
Ooh. My cats kept me up last night. I think if I tried that, I would explode. So I'm going to try something simpler. We might get led to that. We're going to use the guess and check method. Let's do this. Guess e to the kx. Just because the derivative of e to the x is e to the x, so maybe the derivative of e to the kx is e to the kx. I don't know. Let's check. Well, capital F prime of x is the derivative of e to the kx. Now that's going to be a chain rule problem. So my inner function of x is kx. So what's my inner prime? What's the derivative of kx? Like, for instance, what's the derivative of 5x? 5. So the derivative of kx is k. Now, what's my outer function? It's empty. And what's my outer prime?
Outer is e to the x and e to the open and then
Yeah. Yeah, e to the parentheses. So there's my chain rule details. So I get e to the parentheses, that's my outer prime. I put in my original inner function, and then I have to multiply by my inner prime. So the answer is no. But the key thing is, with the guess and check method, you want to articulate what's wrong. What's wrong with this thing that we got? We're off by a factor of k. So we don't lose heart. So let's make guess number 2. It would be little f of x equals e to the kx over k. Because our first guess was off by a factor of k, so we'll just divide it by k and throw it back in. So let's check. Oops, this would be capital F of x. So capital F prime of x is the derivative of e to the kx over k. So again, something that presents like a quotient, you don't need to use the quotient rule. And if you do, you're working way too hard and you might make a mistake. This is going to be 1 over k times the derivative of e to the kx. And we already did that. The derivative of e to the kx is e to the kx times k. Those k's cancel. And that's my little f of x. So, yes. So, you can just keep going down your page. I'm going to add this to our list of rules. Again, you can just keep going down your page. So, this is the e to the kx rule. A particular antiderivative of little f of x equals e to the kx is capital F of x is again e to the kx, but divided by k. Here we go, another one. Find an antiderivative of little f of x equals e to the minus x squared. All right, anybody want to hazard a guess? So you should be getting fearless with the guess and check method. This is not like jumping into the ocean when you can't swim. It's like, you know, it's like wearing water wings and being thrown into the pool by your parents. You're not going to die. So who wants to make a guess? Now the thing about the first guess is you don't want to fret too long. You just want to get something thrown out there, and then it's the second guess you want to be the really good one. Yeah.
How about we just do e to the negative x squared?
Sure. Let's try capital F of x equals e to the minus x squared. Well, let's check. Capital F prime is going to be the derivative of e to the minus x squared. Okay, we're going to have a chain rule thing. We're going to have e to the parentheses. We're going to have our original function inside, and then we're going to have our inner prime. This is the chain rule. How do we do? Well, you want to really hit the reader and yourself over the head with this. This is not equal to little f of x. So that guess is no good. Okay, so what should we use as our second guess? Yeah. Sure. Oh, John? Excellent. Jonah says, let's try this. You know, remember over here, we were off by a factor of k with the first guess, so the second guess we just divided by k, and that guess worked. So guess number 2, we're going to say capital F of x is the same exact thing, e to the minus x squared, but we are off by minus 2x, so divide by minus 2x. And let's check. Capital F prime is going to be the derivative of e to the minus x squared over a minus 2x. Now, I've been ranting all day about how when you get stuff that's presented as a quotient, you usually don't have to use the quotient rule. But actually, this is an honest-to-God quotient rule problem. You got to use the quotient rule. What's going to be on the bottom of the result? So when I use the quotient rule, what's going to be on the bottom?
Negative 2x squared.
Yeah, so minus 2x is the bottom function, and I'm going to square it. And then I'm going to have some stuff on top. I don't know what it is. My cat's kept me up. Well, look, that's not going to be f of x. F of x doesn't have a denominator. Dang it. I have no idea what to make for a third guess. I really have no clue. So let's shelve this. Let's make this our quest. Let's go on from here. Let's put this over here. Quest. Find an antiderivative of little f of x equals e to the minus x squared. I want to put this way over here in the corner. You just keep writing down your page, but I want to put this over here because I want to leave it here. Now, I'm going to send you off with this quest, so I want to give you a diagram of what you're looking for, you know, so you don't come back with the bunny when I sent you out to get a unicorn. So how do we illustrate this? Well, we have our function little f of x. It's e to the minus x squared. Anybody remember what that looks like? That would be minus e to the x. If it was just a function that did this and went down. Yeah?
Does it reflect over the y?
It does have symmetry. The comment was, does it reflect over the y? Notice if you replace x with minus x, you get the same thing. So that means it's symmetric this way. Give you a hint. It starts with b and rhymes with L-shaped curve.
Oh, L-shaped.
Bell-shaped curve. Excellent, Cooper. So here's the bell curve. Or not, I shouldn't say the bell curve. The bell. I'm just going to say bell curve. Because if you throw a Halloween party and say you got to come dressed as bell curve, there are lots of variations. So what we're looking for is capital F of x, which does this. When you find its derivative, we get this. We're shopping for an antiderivative of this, so that's going to be a function who, when you take its derivative, gives you this. You have your hand up, which is a rare thing.
Isn't this the derivative you told us a couple weeks ago?
Oh, yes.
They didn't have an answer.
Yeah, but right now, but you've all forgotten that. So, yeah, so what is this thing going to be that is a function that will go here, that will work as an antiderivative? And it's going to play the role of the function that when you take its derivative, you're going to get here. And the secret is you can't write it. But I'm going to send you off on this snowy day. Some of you are actually, my son would be here wearing shorts and a short sleeve shirt, so applaud all of you for wearing appropriate clothing. But I'm going to send you off into the snow with this quest. In that diagram, you're going to try to find. Okay. Here's another example. I'm going to put this right over here. So again, that quest is this whole thing. Find an antiderivative of little f of x equals 1 over 1 plus x squared. So we're trying to find a function capital F that when I take the derivative of capital F, I get this thing. Any takers? Cooper's got a hand up. Let's wait for some more hands up. Ooh, was your hand up? You're rubbing your eye, but it's all right. You just bought the painting. You're at the auction house and you do this, and that means you bought. Do you have an idea?
X over 1 plus x.
I wish we had time to try that. We have a guess. First guess. X over 1 plus x. But I'm not going to pursue that one because Cooper's got a hand up.
It'd be 1 plus x squared to the negative first, I would say, like in a parentheses.
Well, that's what that is. That's just another way of writing little f. 1 plus x squared quantity to the negative first power. So here's the solution. Capital F of x is tan inverse of x. And remember, that's arctan x. That's because, remember, a couple weeks ago when we were finding the derivatives of really awful things, we found that the derivative of tan inverse x is 1 over 1 plus x squared. So let's draw a diagram of this. So remember that y equals tangent of x looks like this. I'm going to move this way over here to the left. Okay, so that means that y equals tan inverse of x. That means it's the inverse function of that. That doesn't mean 1 over. It means that it's the inverse function. It means you interchange x and y. There's the graph of y equals tan inverse of x. Now apparently, because we did this, when you find the derivative, you're going to get y equals 1 over 1 plus x squared. That's what we just found. A while back, we found that the derivative of tan inverse of x is 1 over 1 plus x squared. So this works this way. So an antiderivative of this is this. Now, anybody remember what the graph of this looks like? It's the coolest thing ever. I've been teaching for this material for like 35 years, and I've actually never gotten to do this example in class. I just never gotten to it. So here we go. The graph of this function looks like this. It's not the bell-shaped curve. It's not even in the family of what we call bell curves, because bell curves are always things that are built from exponential functions. But it sure looks a lot like it, doesn't it? And this thing, we have a formula for this thing, and we have a formula for an antiderivative, an honest-to-goodness formula. And we have a picture of what that thing looks like. So in your quest, I'm sending you off into the snow, you're looking for something that could be an antiderivative here. We don't have a formula for it, but now you even know what it should look like. It should look something like this. It's got to be something that could go up here, when you take its derivative, gives you e to the minus x squared. It's a really cool problem. I often think, who needs the inverse trig functions? But actually, the inverse trig functions are cool because of exactly this example. Because it turns out this is one of the most important functions in the sciences. And the idea that you can't write an antiderivative formula for it, or we sure would like to have a formula for what goes up here, that's really a tough, rich question. And so this is a really cool example because it's very analogous to that. All right. The power rule for antiderivatives. Remember, we're in meeting part 2, which is we're building our list of basic antiderivative rules. So the power rule for antiderivatives says if n is not equal to -1, then an antiderivative of little f of x equals x to the n is capital F of x equals x to the n plus 1 over n plus 1. That's the rule. Okay, well, let's practice this. Or let's exercise this. Find an antiderivative of little f of x equals x cubed. Well, notice that this is a power rule, our power function, with n equals 3. So we're going to use this rule. So we're going to have capital F of x equals x to the 3 plus 1 over 3 plus 1. So that's x to the 4th over 4. Oh, we did that a while ago. We found an antiderivative of x cubed was x to the 4th over 4. That's a particular antiderivative. So now that we have a method for finding antiderivatives, that previous method, the guess and check method, is still an important method. If somebody gives you a function and says, is this an antiderivative of some other function, the best way to answer that is still the check method. Okay, so example. Find an antiderivative of this function, f of x equals 1 over x cubed. Anybody have an idea? Yeah.
We can make it x to the -3rd and then use the product, the power rule.
Exactly. So before we do anything, we have to rewrite f of x as x to the -3rd. That's a power function with n equals minus 4. So I get capital F of x equals, n equals minus 3, sorry. So capital F of x is going to be x to the minus 3 plus 1 divided by minus 3 plus 1. So that's going to be x to the minus 2 divided by minus 2. So that's going to be 1 over minus 2x squared. So that's going to be minus 1 over 2x squared. So notice, it's not 1 over the antiderivative of this. It's not 1 over x to the 4th over 4. You don't find the antiderivative by finding the antiderivative of what's on bottom and putting that on bottom. Also, what's on bottom is not the derivative of this thing. The derivative of 3x of x cubed would be 3x squared. That's not what's down here either. It's 2x squared. So this is a new beast. Now let's check. Capital F prime is going to be, I'm going to use this one, the derivative of that, x to the minus 2 over minus 2, because that's the nicer form for finding the derivative. So the minus 1/2 comes out front, and I have the derivative of x to the minus 2, and so that's going to be minus 1/2 times minus 2 times x to the minus 2 minus 1. So that's minus 1/2 times minus 2x to the minus 3. The minus 1/2 and the minus 2 get together, and we end up with 1 over x cubed. And that is f of x. What I wanted to point out here is that here we used the power rule for antiderivatives. But when we do the check, we use the power rule for derivatives. All right, let's do another example. Find antiderivative of f of x equals x. How do I do this? Well, so notice, observe that my function, little f of x, is just x, but that's x to the 1. So capital F of x is x to the 1 plus 1 over 1 plus 1. So that's x squared over 2. Sure enough, if you take the derivative of x squared over 2, you get x. Okay, find an antiderivative of little f of x is just the number 1. Now, if we're finding the derivative, what would be the derivative of 1? 0. If we're finding the derivative of this, what would be the derivative of this? Okay, yeah, good, okay. So finding an antiderivative is not the same as finding a derivative. Okay, well, notice that little f of x is the number 1, and that's the same as x to the 0. Oh, well, this is a power function, so I can use the power rule for antiderivatives. So x to the 0 plus 1 over 0 plus 1. So that's x to the 1 over 1. So that's just x over 1. That's just x. That does work. If I take the derivative of x, I do get 1. Let's keep going. Let's find the antiderivative of f of x equals 1 over x. All right, somebody want to help me out here? What do I do? Cooper?
You'll have to change it into x to the negative first. But
All right, I'll just stop you right there. I'll just do that. So rewrite. Gabriel's going to complain because I'm writing in red. So then if I use the power rule, capital F of x is going to be x to the minus 1 plus 1 over minus 1 plus 1. So that's going to be x to the 0 over 0. So that's 1 over 0. So I forget, does that equal 1 or does that equal 0?
it doesn't equal anything.
Doesn't equal anything. It's undefined. But why am I writing this in red? This is my blood chalk. This is my actual blood in here. Yeah.
Because it's wrong.
Because it's wrong, yeah. If n is not equal to negative 1, I can do this. But n equals negative 1. So I can't do this. Illegal. All right, well, shoot. I've already sent you out into the cold with a quest to find that thing. At least you're properly dressed. So let's think about what we're looking for here. We're seeking a capital F of x such that, well, it works here. We're looking for a function that will work up here. Something that when you take its derivative gets you 1 over x. Ln of x is very close. So recall that the derivative of ln of x is 1 over x, almost. But it's restricted to x greater than 0. So I had a picture of this I did a while back when we were discussing this. This is the graph of y equals ln of x. And here's a graph of y equals 1 over x. Restricted. It's just the right side of the 1 over x graph. This is one of those things that confused the heck out of me when I was in calculus as a student. But there's another thing that I presented. If I take the ln of absolute value of x, I also get 1 over x. And it's not restricted. And so it looks very similar, except there's kind of a wing on the left side as well. So here's the graph of y equals ln of absolute value of x. And here's the graph of y equals 1 over x, unrestricted. So both of these pictures, when you take the derivative, you get the bottom function. The derivative of ln of x is 1 over x restricted to x greater than 0. The derivative of ln of absolute value of x is 1 over x, but it's unrestricted. Well, the thing is, when you talk about antiderivative rules, you use the second one, the 1 over x rule for antiderivatives. It says this: if little f of x equals 1 over x, then an antiderivative is capital F of x, which is ln of absolute value of x. So I call it the 1 over x rule. And the reason this is the rule that we use is usually when you're given a function 1 over x and you're interested in finding its an antiderivative, it's not the restricted one, it's the unrestricted one. Okay, meeting part 3 is the sum and constant multiple rule. So meeting part 3. This rule goes like this: if capital F of x and capital G of x are antiderivatives of little f of x and little g of x, that just means that if I take the derivative of capital F, I get little f. If I take the derivative of capital G, I get little g. Then this baby, a capital F of x plus b capital G of x, is an antiderivative of this thing. The same a times little f of x plus b times little g of x. Now I have just a couple minutes and I want to write an example. But I'm not going to actually finish this example, but I'm going to set you up for how you should solve it. Find an antiderivative of, it's going to look terrible, sorry, little f of x equals 17x to the 7th plus 13x to the 4th plus 11x cubed. This seemed like a good idea when I wrote it in my office. 7x squared plus 5 squared of x plus 3, all divided by x to the 4th. Yikes. Now you'll notice we have not learned a quotient rule for antiderivatives, and there isn't one. There's a quotient rule for derivatives, but not for antiderivatives. So the solution is we're going to rewrite f of x. So we're going to have 17x to the 7th over x to the 4th. And then 13x to the 4th over x to the 4th. So I'm almost done. I'm not going to solve this. So I'm taking all those separate functions, each of them over x to the 4th. Now, remember, we've had these problems where we want to write things in as power functions, except for 1 over x. If we write 1 over x as x to the minus 1, that doesn't help us. It doesn't help us find the derivative. So f of x I'm going to write as 17x to the minus 3 plus 13 times the number 1. And then this one, I'm going to leave it as 1 over x. because that's something I can find an antiderivative of in the form that it's in. And then this is, and then this should be 17x cubed, right? Yeah. And then this should be 7x to the minus 2, and this should be plus 5x to the minus 7 halves. And then this should be plus 3x to the minus 4. So every one of these things I obtain just by doing rules of exponents. And every one of these things, power function, power function, power function, power function, power function. Every one of these things is something we can use the power rule on, except this one. For that one, you're going to use the 1 over x rule. Okay? Now find capital F of x. And I'll stop there. All right, if you didn't sign in, make sure you sign in back and back. If you were not here on Friday, I've got some of the handouts from Friday.